I would ask the first speaker, Professor Mohamed Gamal, to start his presentation, synthesis and application of multi-wall carbon nanotubes modified membranes for the treatment of processed water. The floor is yours, please. Professor Mohamed Gamal is a professor in the Department of Civil and Environmental Engineering at the University of Alberta in Canada. His research focuses on the fundamentals of advanced and innovative treatment approaches for water and wastewater. His research has resulted in 282 FRE journal papers and 386 conference and workshop presentations. Thank you for joining us today.
Thank you very much. Thanks for the introduction. So the title of my presentation is the synthesis and application of multi-wall carbon nanotubes modified membranes for the treatment of processed water, mainly processed water from oil and gas industry in Canada. And the agenda of my presentation, I'll start with some background, I'll follow up by some membrane characterization data, and then I will follow that with the application of that membrane that's synthesized in our labs for the treatment of the processed water, and finally I will conclude. So the membrane types, I'm not going to go too much into that because we've seen many presentations today, but mainly microfiltration, ultra, nano, and finally reverse osmosis. And you look at the figure on the left-hand side on the bottom there, water pressure normalized flux versus sodium chloride rejection percentage. On the second y-axis to the water runoff, you can see here the different regions for different membrane operations. Ultrafiltration region on the right-hand side, on the left-hand side on the top, the reverse osmosis region, and finally the nanofiltration region on the bottom. The figure on the right-hand side just showing you the normalized pore diameter. And again, I'm sure most of you are familiar with that. If not more expert than me, those ranges of the pore size, basically the average pore size. Regarding the nanotechnology in membranes, so you can incorporate nanomaterials into the polymeric matrix, and this would result in two different things, mainly high water permeability, enhanced mechanical strength of the membrane material, and also would improve the membrane selectivity towards certain ions that you are selectively remove certain ions of the water. And the types of the nanocomposite membranes, either thin film nanocomposites, or we call it TFN, or triple M. The picture on the left-hand side shows you the thin film nanocomposite material. As you can see, the nanomaterials primarily are in the thin film that's covering the membrane of the polymer membranes. On the other hand, in the triple M membranes or mixed membrane matrix, you see that the nanomaterials are actually mixed with the membrane material or matrix, not as a thin film, but all over the membrane material itself. Regarding the various nanomaterials that will be applied as a filler of the nanocomposite membranes, you can have two major families: carbon nanotubes or CNTs, or nanosilver particles. Regarding the CNTs, they have excellent mechanical and electrical and thermal properties and partial antibacterial properties. They can also alter the physical-chemical properties of the membrane material, and the inner pores of the CNTs act as selective nanopores to selectively remove certain like water matrix pollutants or ions, and also they can show improved permeability without an increase in the selectivity of the membrane material compared to other types of membranes. Regarding the nanosilver particles, for sure we know that they are excellent antibacterial agents, so we can add them to the membrane material if you have some disinfection capacity of the membranes. But they can also be incorporated in the membrane as a filler to deactivate the microorganisms during water filtration, thus reducing the membrane bifouling as well. So the objectives of our work was to develop a highly permeable, selective, anti-fouling nano-thin film nanocomposite membranes, and comprising a thin film layer containing silver nano particles, and also a polysulfone matrix containing CNTs. And we also wanted to understand the anti-fouling property of the silver nanoparticles, and finally to investigate the solute rejection antibacterial, and antifouling properties of that membrane. So regarding the preparation of the film nanocomposite membrane, these are the steps. So the polysulfone support layer with and without the multi-wall carbon nanotubes were prepared using the phase inversion casting method, and the thin film nanocomposite membrane was hand cast by conventional interfacial polymerization. As you can see here, the steps are on that slide here. And when we took SEM images of that membrane support layer, and these are the images you can see here. The surface view of the MWMT support layer is shown here, and it showed that the pores, roughly the pore size were in the range of 0.3 to 2 micrometer, and they were well formed throughout the entire matrix. And when we zoom in a little bit to look at the cross-section view of the NTFN membrane, you can see that the NWMTs were depicted as a white mesh in the polysulfone matrix. And when we looked at the transmission electron microscopy of TM images of the support layer and then of the MWMT and also the NTFN membrane, as you can see from both. Slide 1 shows you the winding linear formations of the acid-45 MWMTs that are dispersed and cross-linked in the polysulfone matrix, as evident from that image. And from the right-hand side, as you can see here, the thin film layer containing the silver nanoparticles. Those dark spots that you can see here in the image with the size of several nanometers was about 100 nanometers thin. When we took atomic force microscopy images, you can see here that with silver nanoparticles in the thin layer, the surface exhibited a nanoscale surface roughness, and the root mean square roughness value of the nanothin film composite was about 47 plus or minus 1.5 millimeter. And on the other hand, for the TFN membrane, when we had 10% by weight silver nanoparticles, the membrane slightly increased in terms of the surface roughness, resulting in a root mean square value of about 53.5 plus or minus 2.1. When we look at the XPS spectrum of the two materials, you can see here that the thin film layer coated with the nanoparticles of the silver presented at peaks, at the AG3D52 and AG3D3.5 or 3.2 in the survey scan. On the other hand, the enhanced oxygen content in the C1 peaks is a result of the surface function groups of oxidized MWMTs, and the dotted bands indicated the formation of silver 2O, and AgO compounds. When it comes to the membrane performance, namely the variability of the membranes, as you can see here, that the presence of the MWMTs in the support layer effectively enhanced the water permeability when compared with the sulfone support layer alone by itself. And that was a very good sign of work. By the way, this work was about 10 years ago or so. So we currently don't do much membrane. We can do other things, but this was back in the time when we did a lot of membrane research. So I still have.
You have 10 minutes.
Yeah.
10 minutes. So I would suggest to be 3-4 minutes for.
That's fine.
It's very.
And then the salt rejection characteristics of the two materials. As you can see here, the salt rejections of the NTFN membrane and the other one were very similar actually, but without only the silver nanoparticles. Although the MWMT support layer and the silver nanoparticles film layer can enhance the permeability of the membrane, silver nanoparticle film layer doesn't have significant influence as expected on the salt rejection capacity. And in general, the salt rejection capacity was for the NCL or the sodium chloride was about 88%. For the sodium sulfate is about 95%. For the antibacterial properties, as you can see from the figure, greater than 96% of the attached bacteria on the NTFN membrane, but only less than 3% of the attached bacteria on the NTFC membrane were dead cells. And that tells us that the NTFN membrane exhibited very strong enhanced antibacterial effects as compared to the NTFC membrane. Regarding the stability of the immobilized silver, only about 0.04% of the silver was remobilized after 3 days of soaking. So that tells us that this material is quite stable. But perhaps somebody might ask, but this is not long enough. But use that great material and look at long-term stability and leaching issue of that silver. And regarding the application, in Canada, we have something called oil sands. That's not conventional oil deposits, where actually it's surface, we call it surface mining, where we have bitumen mixed with some water, with some sand, clay, and silt. So that's not conventional oil, basically oil deposit, different than what we have in Egypt or Saudi Arabia or elsewhere. And the oil sands are either loose sands or partially consolidated sandstone containing naturally occurring mixture of the sand, clay, and water, as I said, and bitumen. This bitumen is what we need to separate as oil, right? Source of oil. So the oil sands process water, how it's generated. For that separation of the sand and other soil material from the bitumen, we use something called hot water extraction method. This is where actually method was developed by Prof, who was an engineer in the early 60s in Canada. He was a chemical engineer, and based on that method, we have to add water for that extraction at higher temperatures. And by doing that, then you end up with this process water, OSPW, oil sands process water. This water, both of them are the same thing. So the organic fraction of this water is highly complex. It has like thousands of compounds, many of them BTEX compounds, humic and fulvic acids, benzene, toluene, you name it, plus a group of acetic acid. These are natural occurring compounds, like after millions of years of that, of the formation of this oil containing material. And of course, it has also a lot of the organic materials, including suspended solid, sand, salt, among many other heavy metals, transition metals, and others. So these are the typical characteristics of that oil sands process water. As you can see, the TDS is only about 2,400, which go up to about 3,500, like milligram per liter, but it has many other, constituents. So it's kind of like, I go back again, it's kind of like slightly brackish water. And regarding the in situ pretreatment of OSPW, we take actually this material and we do some pretreatment, and then we go straight to the membranes. And then in this study, we evaluated the low pressure variable membranes with and without acid modified multi-wall CNTs for in situ pretreatment of OSPW before final treatment with high pressure variable membranes. And we did that, we can see that there was some acid modified NWTs that exhibited two peaks, OS and OKLL, that were not present in the pristine NWTs membranes. So peak OS and peak OKLL represent the presence of functional groups in the modified membrane material, and C1S higher resolution scans of the pristine NWTs and acid modified NWTs reveal an enhanced oxygen signal after the acid modification process. And the membrane structure, as you can see here, on the left-hand side, this figure shows the polar structure of the material, and the macro walls are typically asymmetric and dense thick top layer that was developed through the phase inversion process. On the other hand, the acid-treated NWTs were well dispersed in the coated material. And performance with the OSPW treatment with respect to the membrane fouling, you can see here the normalized membrane sample flux reduced to estimated membrane fouling, and the normalized flux basically will stabilize after about 10 hours of filtration. This stabilized flux was maintained for about 24 hours of filtration. And this showed that the NWPs were effective in reducing the number of membrane fouling during the OSPW filtration, and the increased hydrophilicity of the NLPM decreased the hydrophobic interaction between the membrane surface and the foulants in the water that was treated, which helped to decrease the thickness of the fouling layer on the membrane surface. And the permeate flux recovery was, we were able to recover the membrane flux very well from that figure, as you can see. And this actually showed that the recovery of the membrane was higher than that of the LPM after OSPW treatment. And after backwashing, 77.6% and 20.7% of parts decline of the NPM and LPM respectively was recovered. And the fouling resistance, basically, as you can see here, the total fouling ratio and the reversible fouling ratio and the irreversible fouling ratio were estimated as per that figure. As you can see here, the total fouling was about 72% for LPM and LPM was about 56%. The majority of the LPM fouling was due to the irreversible fouling. On the other hand, the majority actually NLPM was reversible fouling.
I would go for conclusions so that we get a chance for two questions.
Yeah, and then the extractable organic fraction, we were very able to remove more than 95% of the acid extractable fraction of the organics out of the water when actually we used the two grade materials. And the organic ions were basically in the range of 80 to 90%. To conclude, the combination of the NM technology and conventional water treatment can significantly improve the quality of the drinking waters with respect to the removal of organic and inorganic contaminants. Inclusion of the nanoparticles into the polymeric matrix has a positive effect in terms of the structure, selectivity, and permeability. The fit-to-purpose porous polymer membranes with enhanced anti-biofouling properties can be fabricated by a varying parameter casting mixture. The membranes with the acid modified NWPs were effective for the removal of foulants in oils and process water. Thank you very much.
Thank you so much. What we want for two quick questions. We'll have one here and then one.
There's support layer on the T layer, right? There's a support layer
Yes.
on the T layer. I mean, there is interfaciation. Support layer on the application.
What?
Interfaciation.
Yeah, we did look into this actually.
And if you use something like 5% of two, right?
Yes.
Thank you.
I'm asking about the mechanical properties after adding natural carbon in several nanowatts. Because you add, I think, very huge quantity of natural carbon to 5% and several nanowatts increase up to 10%.
So the mechanical, regarding the mechanical strength, both of them increased. But I would say the carbon nanotubes has much higher. What's that? No, there wasn't a problem in terms of the flexibility because that's a normal percentage of carbon nanotubes that we added actually for one. It wasn't an issue for us.
We've got room for one last question here.
Yes.
But we can discuss further.
Yeah.
Thank you, Doctor, for the very good contribution. I would like to ask about, have you used one type of process water treatment?
No, that's here in this presentation, but we have different types of the water quality process waters.
Okay.
Just for this study.
How was the efficiency of the pre-treatment of these two lines, especially process water and the porosity of the membrane and the possibility of blocking the pores?
Yeah, there was some blocking involved. I can see from the fouling here, some of some blocks of that, some of the voids, but it's not the point where it's completely blocked. There were some parts, some pores will be blocked, but permanently or the other. But most of them were we were able to cover these pores basically all area like that.
Well, thank you for the interaction, and I would encourage everybody to communicate later after we finish the session.